Okay, so we wanted to show that if you have a target distribution, which is the steady state distribution, you multiply it by the matrix that we had from last time, then you end up getting the same distribution for a given state, that being the key. Target distribution. Oh, it's done. They don't necessarily have to be probabilities, but we can normalize them. I'll just put a constant C. I think your book calls it Z. C. And you multiply that by the matrix. And from last time, so what would the probability be here?
For that corner, P of theta over C. That's P theta, or yeah, 0, staying where you are.
The theta to theta minus would be P minus, and that doesn't work, right?
0.
Theta minus 1 to theta, P plus. Theta minus 1, that's right here, P plus. Theta to theta, P0, P minus, yes. And that's not going to work, 0, P plus, P0, minus, dot, dot, dot. Slide. Looks like Jimi Hendrix matrix. To plot that out of matrix. So P plus 0.5 minimum of the probability that you go to state theta, given or not given, on theta minus 1. Yes. And P minus would mean you go to P theta, theta plus 1. Yes. And P0 would be 1 minus the complement of you going this way or that way. So 1 minus 0.5 minimum of going this way to the left would be minimum of P theta minus 1 over P theta, comma 1 minus 0.5 minimum going to the right, theta plus 1 over theta, comma 1. Good.
Is P minus, it looks like it's stiff. Wait, what?
You can do the same thing, you're just shifting, right? So we're using, I'm using this because I'm looking at state theta, right? And I'm trying to show that we will end up getting P of theta. Now, if you want to look at a different state, this will still change. It'll definitely change theta minus 2 or theta plus 1. Easier way to look at this. It's still the same complement because if this theta happened to be theta minus 1, then that would be theta minus 1. Theta minus 1 plus 1 theta, right? So in terms of relative probabilities, it would end up being the same.
Yeah.
So those two are equivalent.
Okay. So then why write it like that as opposed to?
Because I'm trying to show for this thing. Big theta, because I'm multiplying this by that. So since I'm trying to show that we will achieve P theta over C, I'm writing it this way. If you wanted to go here, P theta 1 plus C, you will be at that point, yes, theta plus 1. You want to go here, you write it as P of theta divided by P theta plus 1 for P minus. And would we have a P plus here? Yes. P plus, for a P plus there, you would write it as P theta plus 2 over P.
Oh, okay, I see, I got you.
So if you multiply that row vector by all of that, we will get 0.5 times minimum of P theta over P of theta minus 1, comma 1 times P of theta minus 1 divided by the normalizing constant C. Yes. The middle value, so I'm looking at state theta, so that needs to be multiplied by P0, agreed? Yes. Row column. So P theta over C times P minus, which is a huge expression. You know, I'll just put P minus. It's okay, we will work our way up to it. And lastly, the other case will be not P minus, P0 plus P theta plus 1 over C times P minus. Let's see. Theta is bigger than theta minus 1. And theta is bigger than theta plus 1. Right? We can only show this by picking cases, yes? Because things are random. Let's start with the first case. If theta is bigger than theta minus 1, what would happen? We'd end up getting 0.5 times P theta minus 1 over C. Because P of theta would be bigger than P of theta minus 1, end up getting 1. P0, well, I've got 1, so 1 minus 0.5 what do you think would happen here?
The minimum would be P of theta minus 1 over P of theta.
So it's P of theta minus 1 over P of theta. The next one, minus 0.5. Theta plus 1 is less than P of theta. So that would also turn into theta plus 1 over theta. Yes. The last term theta plus 1 over C multiplied by 0.5, minimum of P of theta over P of theta plus 1. That's bigger than that term. So that would turn to 1 or become 1, so that'll be 1. Yes? So we will have 0.5 P theta minus 1 over C plus P of theta over C minus 0.5. Multiply those two, you would get P of theta minus 1 over P over C. P of theta would get cancelled. Distribute to this term, you would have 0.5 P of theta plus 1 over C. P of theta will get cancelled. And lastly, you would end up getting 0.5 P of theta plus 1 over C. Yes? That term will go away. That term will go away. We'll simply end up having P of theta over C. So when we are at state theta, this is the case, the probability that you are in state theta is whatever we had P of theta divided by the normalizing constant. So that is our target distribution. If that is the target distribution at state theta, we end up getting the exact probability. Yes, we converge to the same value.
And does that make sense because the probabilities are greater, and so I'm thinking if we're already at theta and it's greater than theta minus 1 and theta plus 1.
No, we can have other cases too.
Right.
Well, we'll do it.
But for this case specifically, the reason why the probability is because it's greater than the because P of theta is greater than theta minus 1 and theta plus 1, we're not even really considering going to those states. We're thinking,
right.
Yeah.
So this ends up being, the same state. Now, what the logic here is at state theta plus 1, if we follow the same process, we will end up getting P of theta plus 1 over C. So eventually, if we have a steady state distribution here, which is our target distribution, when we multiply it by the transition matrix, we would end up getting the exact same probability. Let's pick one more case. There are 4 cases. Let's not do all 4 of them. Which one should we pick?
Where P is between them.
Between? No, that would not work.
P is smaller.
So we just have to make one decision. So we'll keep that. We will change that to this. This. Let's see if it works out. I'm thinking it should, but we will see.
I mean, pretty much pick between them.
Huh?
Yeah. Like that is between.
That is between. That's about not work, better work. Okay. So same logic, so 0.5. So P of theta minus 1 over C times P plus, and we have P of theta bigger than P of theta minus 1. So that would be 0.5 P of theta over P of theta minus 1 plus P of theta over C 1 minus,
Theta is bigger than theta minus 1, so wouldn't that just be 0.5?
theta is bigger than
Yeah.
minus 1, yes. Thus,
Of course.
and the second case, 1, P of theta is bigger than P of theta minus 1, so that would be the smallest term. So minus 0.5 P of theta minus 1 over P of theta. Over here, theta is less than theta plus 1, so that would be 1 minus 0.5. Good. The last case, we have P of theta less than P of theta plus 1, so we'll have that. So P of theta plus 1 over C multiplied by 0.5. That's correct. P of theta over P of theta plus 1. Yes. Let's see. Does it work out? That'll work out. So those two will get cancelled. So we'll have P of theta minus 1 over C times 0.5 plus P of, by distribute, I get P of theta over C minus 0.5 P of theta minus 1 over C minus 0.5 P of theta over C plus 0.5 P of theta over C. Yes?
That's 2 cancel out, and it looks like the first and the third.
So those two will cancel out, those two will cancel out. We'll end up getting P theta over C. Yes. Now you could test another case. You could do P of theta less than P of theta minus 1 and P of theta greater than P of theta plus 1. And you can do both of them being less, end up being same P of theta over C. This is working because we are looking at state P of state theta. Now, P plus, P minus, and P0 must be defined in a different way if you have to do the same thing for state theta minus 1. And if you want to do it for state theta plus 1, you would redefine this again. But the idea is quite simple. You just plug in theta plus 1, right? And then you're set. So this would become theta plus 1 over theta. That would become theta plus 1 over theta plus 2, because you're moving to the next state, yes? Theta over theta plus 1, theta plus 2 over theta plus 1, right? So in that way, you can prove it for the next state, theta plus 1, and so forth. So the conclusion here is depending on the state that you pick, whatever probability that you have would end up being the exact same probability, no matter which case you pick. And that is true as long as you have the target distribution, which is our posterior distribution. The C's are, the C is the normalizing constant. Good. So that is the Metropolis algorithm in a discrete easy sense.